Hi folks, here is one of your last Learning Target videos for Learning Target 16. We're going to do a very brief introduction of redox reactions, oxidation reduction reactions, and then we're going to blow past this and we're going to move right on to organic chemistry. But for this Learning Target, we want to talk about oxidation and reduction just briefly so you'll understand some of the stuff we discuss with the OChem unit. So the purpose of this video is to review oxidation reduction values from valence electrons, which you have learned before, you just might not remember. Identify oxidizing and reducing species, and identify oxidizing and reducing agents. So here we go. You're going to want your periodic table for this particular learning target. And you're going to make some recollections here. Hopefully you can recall way back before the pandemic when we were doing valence electrons. You will notice that your periodic table is broken up into groups, and there are A groups and there are B groups. The A group elements indicate the number of valence electrons. So for instance, group 1A means everything in this group or column has one valence electron. The B group elements, you might recall, are a little bit more difficult to discern their valence electrons numbers because they are transition elements. That means they could have variable oxidation numbers, and that's going to play a role here when we move forward with the rest of this lesson. So this part is all review. You may recall that elements want to gain or lose electrons in order to obtain an octet of electrons in their outermost shell. So I'm not going to go through all of the details involved with electron configurations in order to figure out where the octet comes from. In a nutshell, just know that A group elements with less than 4 electrons will lose electrons to make an octet, and however many electrons they lose, that will be their oxidation state. They will have a positive charge because they lost electrons, which are negative particles, and they are considered cations. Group A elements with more than 4 electrons will gain electrons to make an octet. They will be assigned the oxidation state with however many electrons they would like to gain. They will have a negative charge because they gain those negative particles, and they are called anions. And if you've got an element that has exactly 4 electrons, you will notice that they could be cations or anions, and it's all based upon what they're paired with. So here's an example of chlorine and sodium, just to show you once again how we indicate the valence electrons for these particular elements. I look on the periodic table and I notice sodium is in group 1A. That means it has 1 valence electron. You might remember that this is its Lewis dot structure. 1 is definitely less than 4. So that electron will go somewhere to become a cation, and the charge, since it lost 1 electron, will be +1. Chlorine is in group 7A, so it has 1, 2, 3, 4, 5, 6, 7 valence electrons. This one is much easier to see that it's going to make an octet because that 1 electron, maybe from sodium, will come into the chlorine to make an octet, 2, 4, 6, 8 electrons. Since it gained 1 more electron, it's going to have a -1 charge. And that's why sodium and chlorine are a match made in heaven, because 1 sodium can give its 1 chlorine 1 electron to chlorine to make an octet. And that would be what the ionic Lewis structure would look like. So this was just a quick review to remind you where we get those oxidation states from. So when we're talking about oxidation numbers, there's some really important rules to remember. I would definitely pause your video and take notes on these following bullet points. So, bullet point number 1, elements have no oxidation state because they have not given up or taken any electrons. So elements will always have the oxidation state of 0. This includes diatomics. Have no fear of ice cold root beer. You might remember that. Hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, bromine. Hydrogen could have a charge of +1 or -1, even though it's in group 1A, but it depends on what it's paired with. And I'm going to show you an example of that a little bit later on. Oxygen will always be a -2 oxidation state unless it's in a peroxide, like hydrogen peroxide. When you are trying to find the oxidation numbers of individual elements in a compound, know that neutral compounds will have a total sum of oxidation numbers of 0. And I'll show you an example of that in a moment. The sum of the oxidation numbers in a polyatomic ion will add up to the overall oxidation number. So this might indicate to you, you might need to go and dig out that polyatomic table you might not have seen in a year. And overall, the oxidation state of all other ions can be determined based upon the rules above. And it turns into a logic puzzle. You fill in what you know first, and then you solve for what you don't know. So like I said, here's your challenge. I would pause your video and definitely take a look for this. Can you find your polyatomic ion table? If you can't, no worries about that. You can print it off. If you need a copy, you can come and get it in person. And if you are a remote C person, I will put it in the pickup box outside of the school. So let's practice now calculating some oxidation states. And I gave you 3 examples here. Try to figure out what the oxidation state is for each of the elements in these compounds. So let's start with KMnO4. So this is called potassium permanganate. I don't care how to write out the name for this right now. Just know it's potassium with a charge of +1. I get that +1 charge directly off of my periodic table. And so here's potassium here. It's in group 1A, so it has a +1 charge because it'll give away that 1 electron. Permanganate, I will look on that polyatomic table and find that that whole entire polyatomic ion has a -1 charge. So that's great. I've indicated the oxidation state for one of the elements, but I have to do it for everything inside of this polyatomic as well. So to do that, I'm going to break it down. I know that an Mn plus 4 oxygens have to equal -1. Well, 4 oxygens is going to be a 4 times a -2, which is going to give me -8. And so manganese has to be, if this is going to be a -8, this is going to have to be a 7 in order for the answer to be -1. And I know that that oxygen is -2 because it's not in a peroxide, meaning it's not looking like H2O2. And I know that the manganese has to be a 7 in order to balance out everything for the MnO4 to have the overall charge of -1. So this is going to be a +7. So that is how we try to use deductive reasoning in order to figure out the unknown oxidation number if it's a transition metal. Let's look at hydrogen peroxide over here. Here's the reason why hydrogen peroxide is going to not have oxygen have an oxidation state of -2. In this case, I have to think about which element is more electronegative. And we haven't talked about that in a year as well. But hydrogen is definitely less electronegative, wants electrons less than oxygen, because oxygen is one of the most electronegative ions. That means that the hydrogen has to have a positive charge, and if it's positive, it'll be +1. And that means that both of these oxygens, since I have two hydrogens here, let me back up, this has to be a +2. That means that both of these oxygens have to total -2. That means that each oxygen, which there's two of them, have to have a -1 charge in order to balance this out. So what we have just shown is that hydrogen has a +1 charge, and in a peroxide, like H2O2, oxygen will have a -1 charge. This is a rarity. And then we're going to look at an example where hydrogen is actually going to be negative in this case. Thinking back, I'm going to think to my electronegativity trends, and I know boron is a metalloid, hydrogen is a nonmetal, so boron is going to be less electronegative than the hydrogen in this case. So that means that if hydrogen is more electronegative, it's going to have its -1 charge for a total of -3. That means boron has to have a +3. So it's just as simple as that. And we'll go through and see a lot more of these examples as we roll on through the presentation. So here is a big beastie question. I want to figure out the oxidation state of this iron that is contained in this complex transition hydrate, which we aren't going to get to transition hydrates. If you roll on with chemistry one day, you will figure out what these things are. So this looks like a really complicated problem, but I promise you it is not. Because I can look on my polyatomic table and realize that this whole thing, NH4, ammonium, has a +1 charge. I can look at my polyatomic table and realize that sulfate, SO4, has a -2 charge. And I know that water, H2O, is a compound that is neutral with no overlying oxidation state, so it has to have 0 charge. So I know that all of these things have to add together to 0. So I have a 2 times a +1 plus whatever my Fe is going to be, plus 0 times 6, because water has a 0 charge and I've got 6 of them, plus 2 times a -2. So I'm going to end up with 2 plus whatever my Fe is going to be, plus -4 has to equal 0. So doing my math here, I realize that the Fe has to be +2. It's +2 plus 2 minus 4 equals 0. So that is going to be my oxidation state for my Fe. I'd write the answer as Fe +2. So let's look at our next slide. So how does this work in chemical reactions? So there are two little anagrams for you to remember how to identify what is oxidized in a chemical reaction and what is reduced in a chemical reaction. I like the first one because it's so dramatic. It's Leo the lion says, grrr. So loss of electrons is oxidation. That's for Leo. Loss of electrons is oxidation. Gain of electrons is reduction. Grrr, gain electron reduction. I like that one, but if you don't like to make sound effects, then you can use oil rig. And oil rig just means oxidation is loss of electrons, reduction is gain of electrons. Important phrases to remember when you're looking at chemical reactions. So here are two chemical reactions here. We're going to go through and we're going to decide what is going to be oxidized and what's going to be reduced. So in order to decide what's oxidized and what's reduced, I'm going to go through and fill in oxidation states that I know. So I'm looking at my periodic table. I realize sodium here is represented by an element. So it's going to start with an oxidation state of 0. I know that in water is neutral, it has no overall charge, and oxygen in this case is going to be a -2, and hydrogen is going to be a +1. Notice that I'm not paying a bit of attention to the coefficients out in front. The coefficients out in front with these reactions have nothing to do with what we're doing today, so I could care less of how we've balanced this chemical equation. On the product side, now the sodium is bonded to the hydroxide. Hydroxide, I'm looking at my polyatomic table and realize this whole thing has a -1. I put it in parentheses to indicate to you to remember to look at your polyatomic table. So sodium has to have a +1. And hydrogen has turned into its elemental form, so it's going to have no charge. So if I take a look here, hydrogen went from a +1 to a 0. That is making it more negative, so I added electrons. So hydrogen must have been reduced. Oxygen, however, goes from a -2, and in here it's still going to stay a -2 because hydrogen's going to be a +1 and oxygen's going to be a -2. So oxygen, nothing happened, so it's going to stay, and I'm just going to say it's going to stay the same. The other piece here is the sodium, and sodium went from a 0 to a +1, so it got less negative, so it had to be oxidized. Loss electron oxidation. So sodium in this case was oxidized, and hydrogen in this case was reduced. If everything had the exact same oxidation state as where it started, then it's not a redox reaction. It's not an oxidation reduction reaction. And here's this example of the decomposition of hydrogen peroxide again. I decided to do this one because it's not always straightforward with having one oxidizer and one reducer. So we decided in a previous example that hydrogen has a +1 in this case, and oxygen has a -1. In water, hydrogen has a +1 and oxygen has a -2. But in oxygen in its elemental form, it's going to be 0. So oxygen here is doing a couple of really weird things. Oxygen is going from a -1 to a -2 and a 0. So it is being oxidized and reduced at the same time. So you're going to have an oxidation and a reduction going on. And hydrogen, nothing happens, stays the same. So those are a couple of examples of how to come up with your oxidation states and decide what's being oxidized and what's being reduced in chemical reactions. All right, so in a redox reaction, you always have something that's oxidized, you're always having something that's reduced, and one of the species is doing the other opposite thing to the other species. So for example here's my sodium being thrown in water again to make sodium hydroxide and hydrogen gas. I didn't balance the equation. From the last slide, we saw that sodium is being oxidized and hydrogen is being reduced. That means we're going to call hydrogen here the oxidizing agent. And it's the oxidizing agent because it is taking electrons from the sodium. The oxidizing agent takes the electrons from the species, and in the process, the oxidizing agent is being reduced. So whatever's being reduced is the oxidizing agent. On the flip side, sodium is going to be your reducing agent. It's going to be your reducing agent because it's giving the electrons to the hydrogen. So in this case here, since the sodium is giving its electron to the hydrogen, sodium is the reducing agent and is being oxidized in the process. So whatever's being oxidized is the reducing agent, and whatever's the reducing agent, or whatever's being reduced, is going to be the oxidizing agent. So with that being said, hopefully this was kind of clear. And there's going to be a simple attached practice worksheet on this learning target 16. Hope you enjoyed yourself, or at least it's an easy thing to end the year with. We're almost done. Hang in there. See you soon.